Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Hello. In this problem, which seems rather difficult, it's mostly going to be relying on the information we learned about the nature of magnetic forces for current carrying wires, and thinking back about Newtonian physics and doing some Newton's second law analysis. So we have this diagram in the book, but I'm going to draw it in different ways here for us to get a good idea of what is going on. Right, so what's going to happen is this rod is going to start to slide down these conducting rails, and it's going to then start, because of the magnetic force, a current is going to start to flow. So ultimately, we're going to be having, from a top view, so looking down on this thing, right, we're going to have this rod, and it's going to be sliding down the incline. We'll say down the incline is to the left at some constant velocity, because as it starts to slide, some current begins to build up. And then, because our magnetic field in this case, if we're looking down on this, is heading out of the page, if we do that, then we see our right-hand rule tells us that if our pointer finger follows the current and we rotate our wrist so that our middle finger is heading out of the page as the magnetic field is, then of course our thumb is heading back into the right. So we have a magnetic force that is heading directly to the right in this case, and that's going to be something that helps to counter, right, the part of gravity that is pulling this thing down. So we have some part of the gravitational force that is making this rod slide down the incline, and then another part of the magnetic force that is trying to keep this rod from sliding down the incline. So what we're going to do now is draw a free body diagram for this rod sliding down this incline and then do a Newtonian analysis on it. So let's kind of redraw what's going on in the book, but from a side view, right? So we have basically, though it's a rod, we're going to consider it an object sliding down an incline, and we know the angle here is 30 degrees. So we have an object here sliding down an incline. And so let's think about what the forces are going to be and in what directions. Now, of course, we're going to have a normal force that is perpendicular to the surface like this, and our gravitational force is going to act directly downward. Now, I'm not drawing the vectors in any particular lengths. I'm mostly drawing them so that the diagram looks good. Now, remember, so if the rod is sliding down this way at this constant velocity v, then that means the current is going to be heading into the page here. So the rod's current is going to be heading into the page. Now, again, we have a magnetic field that is directly upward and a current that is directly inward. When we do our right-hand rule there, just like we saw that the magnetic field is directly to the right on our left diagram, that means, again, it's going to be directly right here. So the magnetic force is trying to push this rod directly to the back of our incline. Maybe write that again. The back of our incline. So that is our free body diagram. Now what we need to do is do a little bit of balancing. So we know, because the velocity is constant along the incline, we know that the net force along the incline must be zero. The net force along this incline must be zero. So if we can figure out the components of the forces that are acting along the incline, we can balance those components and then hopefully solve for what we want to know, the current flowing through this wire. Because we know the current is related to the magnetic force, and the magnetic force is going to be part of the net force along the incline. So let's try to break these vectors down into the components that are along the incline. Let me just do a little redraw here to make things a little nicer. So if our incline is along this direction here, right, let's set up a coordinate system where 1 is along the incline, right? We want to balance all of our forces there. We know the force is balanced because the velocity is constant. Now, the normal force has no component along this direction along the incline, what I've called the x direction. So we don't have to worry about breaking that force down to any sort of components. But the weight of the rod, which is headed straight down, will of course be able to break that down into a component that goes along the incline, right? We have a component this way of the gravitational force and a component this way for the gravitational force. If you remember back from physics 1, the component of the gravitational force that goes down an incline is given by, if this is the incline angle theta, mg sine theta. That's the component of gravity trying to pull the object or rod down the incline. Now remember, we have a magnetic force directly this way, and because it's directly horizontal and we want to break it down into a component along the incline, this theta here is the same theta as the incline angle. So if we draw a little triangle here, we see that we want actually the adjacent component because our total magnetic force makes up the hypotenuse of this triangle. So if we want to project that onto here, we need the cosine part. So if we take the magnitude of our magnetic force, multiply it by cosine theta, we're going to get the component that goes back up along the incline. And remember, we found the component of gravity that goes down the incline. So because, again, just remind ourselves that because the velocity in this direction is constant, that implies that the net force in that direction is 0, right? Because ma must also be 0. Your acceleration is 0. Write the word net better. Okay, so if we balance these forces in this direction, we get this particular equation, right? So in the plus x direction along the incline, I have this component of my magnetic force, cosine theta, and so that's going up the incline. That's a positive component of all my forces here. Going down the incline is the component of gravity, mg sine theta. And those, of course, must balance, so must add up to be 0. And that means we can equate the two together. So let's solve for this. We actually can plug in an expression for the magnitude of the magnetic force, right? We know that for a current carrying wire, the magnitude of the magnetic force we see is I times, so the current through the wire times the length of the wire times the magnetic field through which the wire is moving times sine of phi, the angle between the magnetic field and the current. And then we all have to multiply that by cosine theta. Then we finish out our equation, minus or equal to mg sine theta, because we put move that term over to the other side. Now, this phi angle, what is the angle between the current and the magnetic field? Well, we know that's 90 degrees, so this sine of 90-degree term is going to go to 1. So we want to solve for the current. We want this particular value here, so let's solve for it. That means I is equal to mg, so the weight of our rod, times sine of the angle, so the angle is 30 degrees, and then we have to divide by L, B, and cosine theta. So what do? We know all of these things, right? We know the mass of this object. The mass of the rod is 0.2 kilograms, 0.20 kilograms. The acceleration due to gravity is 9.81 meters per second squared. We multiply by a sine of the incline angle, which is 30 degrees. Divide this by the length of the rod. We're given that. It's 1.6 meters. The magnitude of the magnetic field is 0.050 teslas. And we divide that by cosine of our 30 degrees. Plug all those things into our calculator, and we see that we get an answer for a current flowing through this rod such that it's falling at a constant velocity is about 14 amps.